We decide to build the biggest scientific experiment ever built, 16 miles in circumference underneath Geneva. We accelerate protons, which are these simple particles, to 99.999999% speed of light. In every collision, we create the conditions that were present less than a billionth of a second after the Big Bang. We take photographs of those 600 million collisions per second. Scientists often engage in experiments that carry risks and occasionally lead to unexpected and deadly consequences. In certain movies, this theme is exploited, portraying scientific experiments gone wrong and giving rise to either monsters or heroes. Recently, Earth's magnetic field encountered pressure as a result of an experiment conducted by scientists, and it caused an unexpected crack in its structure. Shortly after the activation of the Large Hadron Collider, while magnetic monopoles may not hold immediate significance for the average person, scientists are deeply fascinated by their potential impact on the universe. Hence, considerable effort is invested in the search for these peculiar objects. Now, what's more unsettling is that scientists from Cern are conducting an experiment at the South Pole, which could just result in unexpected outcomes. Famous British physicist Brian Cox, who works at Cern, recently revealed the details of this experiment, which shocked the whole world. So, what is the origin of the concept of monopoles, and what are their potential effects on the universe? What terrifying experiment is being conducted by certain scientists at the South Pole? Let's go back to the late 1800s, when we didn't know much about electricity and magnetism. People believed in two types of electric charges, where similar charges pushed away and opposite charges pulled together. When these electric charges moved, they created what we now call electricity. We also understood permanent magnets, which had a north pole and a south pole. However, no matter how small you cut a permanent magnet, you'd never end up with just a north pole or a south pole. In simple terms, magnetic charges always come in pairs, like a duo. During the 1800s, several discoveries helped us understand the electromagnetic world better. We learned about induction, where moving electric charges create magnetic fields, and how changing magnetic fields create electric currents. We also discovered electromagnetic radiation, realizing that accelerating electric charges emit light with different wavelengths. Combining all this knowledge, we found that the universe wasn't symmetrical when it came to electric and magnetic fields and charges. Maxwell's equations only included electric charges and currents. There were no basic magnetic charges or currents. Interestingly, all magnetic properties we observe are actually caused by electric charges and currents. If we look at it mathematically or from a theoretical physics perspective, it's easy to tweak Maxwell's equations to include magnetic charges and currents. Just introduce the concept that objects can have a fundamental magnetic charge, a standalone north or south pole. When you add these extra terms, Maxwell's equations change, becoming entirely symmetrical. Induction now works both ways. Moving magnetic charges create electric fields, and a changing electric field can induce a magnetic current, making magnetic charges move and accelerate within a material, carrying a magnetic current. For quite some time, these ideas were more speculative until we started understanding the significance of symmetries in physics and the quantum aspect of the universe. There's a possibility that electromagnetism shows symmetry between electric and magnetic components at a higher energy level, and our reality might be a lower energy version with broken symmetry. Although Pierre Curie acknowledged the existence of magnetic charges in 1894, it was Dirac in 1931 who demonstrated something remarkable. If there was even one magnetic charge anywhere in the universe, it would quantum mechanically imply that electric charges should be quantized everywhere. This is interesting because, in the case of quarks, not only are electric charges quantized, but they're quantized in fractional amounts, a powerful indication in physics that new discoveries might be on the horizon. However, it's essential to note that none of this proves the existence of magnetic monopoles, it simply suggests the possibility. Scientists, however, haven't given up on the search for monopoles, and this persistence is crucial. When scientists explore a theoretical concept, one thing they examine is pathologies, reasons that could potentially disrupt the universe based on the scenario they're investigating. When Polyakov monopoles were initially proposed, a significant issue surfaced, a phenomenon known as overclosing. In the early universe, conditions were sufficiently hot and energetic for the creation of any particle-antiparticle pair with enough energy. Symmetry breaking could either assign a non-zero rest mass to a previously massless particle or spontaneously generate numerous particles or particle-antiparticle pairs from the vacuum. The former occurs during Higgs symmetry breaking, while the latter happens when the Pecchi-Quinn symmetry breaks, allowing axions to emerge from the quantum vacuum. Both scenarios could have severe consequences. Normally, the universe expands and cools with energy density closely tied to the expansion rate. Introducing a significant number of previously massless particles with mass or spontaneously adding numerous massive particles rapidly increases the energy density. This disrupts the balance between expansion rate and energy density, leading to an excess of material in the universe. Consequently, the expansion rate not only decreases, but, in the case of monopole production, drops to zero before contracting. In a short time, the universe collapses, resulting in the Big Crunch, termed overclosing the universe. In 2018 at the LHC, a novel approach involved colliding heavy ions in the form of lead nuclei, each containing hundreds of protons and neutrons. Unlike single proton collisions, these collisions occur at lower energies. When these lead nuclei closely interact or collide, they generate an extraordinary outcome, the universe's most powerful magnetic field, reaching up to 1,000,000 times the strength found in neutron stars. Although these fields endure for a brief duration, they present an alternative mechanism for producing magnetic monopoles. The theory draws parallels with the process of generating electrons and their antimatter counterparts, positrons, offering an electrical analogy to the concept of monopoles. As per the Schwinger mechanism proposed in the 1930s, a potent electric field can engage with quantum fluctuations in a vacuum, resulting in the generation of electrons and positrons. Similarly, a robust magnetic field is anticipated to produce both north and south monopoles. Although no evidence of monopoles was identified, an unusual revelation was made. A breach in the Earth's magnetic field manifested and persisted for approximately 14 hours. This extraordinary occurrence was attributed to a co-rotating interaction region, CIR, originating from the Sun. A CIR is an extensive plasma structure that materializes when swift and sluggish solar winds interact within the heliosphere, low and middle latitude regions encompassing the solar magnetic field and solar winds. Comparable to coronal mass ejections, CMEs, CIRs are propelled from the Sun towards Earth and may evolve into shock waves and compressed magnetic fields, resulting in turbulent space weather. This phenomenon is often visually manifested as striking coronal mass ejections, similar to solar flares. CMEs result from the entanglement and rearrangement of the Sun's magnetic field through magnetic reconnection. When magnetic field lines become entwined, they generate concentrated localized magnetic fields capable of penetrating the Sun's surface in active regions, leading to CMEs. These events typically coincide with Sun spot groups and may be accompanied by solar flares, though not always simultaneously. CMEs are similar to solar flares and are most prevalent during solar maximum, a phase in the Sun's 11-year cycle of heightened activity. These events expand in size as they traverse away from the Sun. Larger CMEs can occupy nearly a quarter of the space between Earth and the Sun by the time they reach our planet. If a CME is sufficiently large and travels faster than the solar wind, it produces a shock wave in which accelerated charged particles precede the CME. Disrupting space weather conditions and intensifying geomagnetic storms. Although CMEs generate beautiful auroras, their potential for destruction is noteworthy. Substantial CMEs can induce technological malfunctions, presenting significant challenges in the contemporary world. The Carrington event in 1859, for instance, disrupted the global telegraph system, with reports of operators experiencing electric shocks and telegraph machines emitting sparks, leading to ignited papers. In a more recent incident, a CME accompanied a solar flare in 1989, causing a 12-hour electrical blackout throughout the entire province of Quebec, Canada, resulting in at least $10 million in damages to Hydro-Quebec, the utility company. The havoc wreaked by CMEs is attributed to their ability to induce electrical current surges, overwhelming power grids, and causing widespread blackouts. Additionally, these events perturb the Earth's magnetic field, impeding radio transmissions and elevating radio static in the ionosphere. Ionosphere disturbances during CMEs pose a particular threat to GPS systems, leading to deviations of GPS coordinates by tens of feet. GPS relies on radio signals between satellites and ground receivers, and the signal passing through the ionosphere containing charged plasma undergoes bending, similar to lenses bending light. While GPS systems can typically compensate for this bending, CME-induced disruptions can be severe enough to compromise GPS accuracy, rendering receivers unable to calculate precise positions. Earth-orbiting satellites, particularly those in high geosynchronous orbits where many communication satellites are positioned, are also vulnerable to the impact of CMEs. Satellites face the risk of encountering a high current discharge or suffering damage from high-energy particles penetrating their systems during space weather events. When geomagnetic storms induced by CMEs occur, susceptible satellites can be placed in safe mode as a precautionary measure to avert electronic damage. SpaceX experienced the impact of space weather firsthand when a geomagnetic storm destroyed approximately 40 Starlink satellites, amounting to a loss exceeding $50 million, in February. New insights into the Earth's magnetic field revealed that it stays open for hours during solar storms, contrary to the previous belief that these openings were brief. Analogous to a drafty house during a storm, the magnetic shield deflects the majority of space storms, but some energy escapes, causing issues with satellites, radio communication, and power systems. However, this description does not align with our reality. We persist, and there has been no collapse. This predicament is recognized as the monopole problem and constitutes one of the three primary motivations for cosmic inflation. Analogous to how inflation stretches the universe to a state nearly indistinguishable from flat, addressing the flatness problem and imparting uniform properties across our observable universe to solve the horizon problem. It can also resolve the monopole problem, provided the universe doesn't heat back up beyond the grand unification scale after inflation concludes. How have scientists pursued the detection of magnetic monopoles? In 1981, experimental physicist Blas Cabrera devised a cryogenic experiment featuring a specially designed coil of wire to explore the existence of magnetic monopoles. His rationale involved constructing a coil with 8 loops, anticipating a distinctive signal during the passage of a magnetic monopole through the coil due to induced electric currents. When one end of a permanent magnet moves into or out of a wire coil, it induces a current. However, if a magnetic monopole traverses the coil, it should induce an electric current precisely 8 times the theoretical value of the monopole charge, given the 8 loops in his experimental setup. Distinguishing scenarios, if a dipole passed through, would yield a signal of +8, followed by a signal of -8. On February 14, 1982, with no one monitoring the experiment, Cabrera returned the next day to discover a single signal remarkably similar to what a magnetic monopole should produce. This sparked considerable interest. Did this challenge the validity of inflation, suggesting a universe with magnetic monopoles? Alternatively, did it affirm inflation, proposing that the one monopole expected in our universe happened to traverse Cabrera's detector? Or was it a manifestation of experimental errors, a glitch, a prank, or an unexplainable anomaly? Subsequent experiments emulating Cabrera's approach, but often larger and with extended runtime, failed to observe anything resembling a magnetic monopole. Nevertheless, the pursuit of monopoles continues with the dedicated efforts of Cern and its scientists. The Large Hadron Collider, LHC, stands as the world's largest and most powerful particle accelerator, situated at Cern, comprising a 17-mile or 27 kilometers ring of superconducting magnets and a series of accelerators. The LHC propels high-energy particles through its structure with remarkable force, akin to a bullet fired from a gun. Positioned 328 feet below ground, the collider directs a beam of protons in one direction while an opposing beam travels in the opposite direction. At peak velocity, these particles collide at an astounding 99.9999991% of the speed of light. Upon collision, a wide range of particles is generated, many with a lifespan of less than a second. However, they leave a trace of subatomic clues that scientists meticulously follow. Utilizing two detectors, including the notable Atlas, scientists unravel the trails, providing insight into the fundamental constituents of our universe. Atlas, measuring approximately 148 feet in length and 82 feet in height, played a significant role in the discovery of the Higgs boson. Remarkably, Atlas is half the size of Notre Dame Cathedral and twice the weight of the Eiffel Tower. Scientists leverage Atlas and other detectors like ALICE, CMS, LHCb, and LHCf to explore realms often relegated to science fiction. These investigations delve into intriguing questions such as the existence of other dimensions, the nature of unifying forces in the universe, and the quest for evidence of dark matter. Atlas and CMS stand out as the exclusive detectors devoted to uncovering the mystery of the Higgs boson at the LHC. Collaboratively operated by a global team of scientists, each experiment at the LHC contributes unique insights. While colliding particles at nearly the speed of light provides valuable information about the inner workings of atoms and the forces that bind them, interpreting the copious data generated by these collisions poses a considerable challenge. With particles colliding at a rate of nearly 600 million times per second, the detectors, such as Atlas, are selective in the data they record. Atlas, for instance, could amass data equivalent to 100,000 CDs every second, but it selectively records about 27 CDs per minute. During the reconstruction phase, scientists scrutinized their theories by comparing computer-simulated collisions with real-world collisions, looking for disparities that could unveil new scientific insights. The data center processes 1 petabyte of data daily, requiring 223,000 DVDs to store the information. Within a petabyte, with scientists sifting through 30 petabytes of data annually, the quest for new scientific discoveries becomes a formidable task. A novel class of experiments at the Large Hadron Collider, conceptualized by imperial physicists, has created conditions more conducive to producing monopoles. Although no monopoles have been discovered to date, these experiments enable researchers to refine their understanding of the potential properties of monopoles, charting the path for future investigations. The ability of physicists to draw conclusive insights from past experiments, both at the LHC and elsewhere, has been constrained. However, these recent experiments employing a distinct production mechanism offer a decisive refutation of the existence of specific monopole types. They significantly enhance our understanding of the potential directions for the monopole search. As the Sun approaches its most active phase in the solar cycle around July of 2025, displaying unusual activity for this early stage, there is an increased likelihood of witnessing the aurora. This heightened solar activity raises concerns about the potential effects on Earth's magnetic field. One of the most alarming consequences of losing Earth's magnetic field could be the impact on the air we breathe, with a solar wind emerging as a potential culprit in such a scenario. Once more, the Sun's potent solar wind possesses the capability to strip gases from a planet's atmosphere, a phenomenon likely responsible for the transformation of Mars. Mars, once resembling Earth with abundant water and a dense atmosphere, lost these features when its magnetic field disappeared billions of years ago. The unprotected atmosphere was gradually torn away into space as atmospheric pressure dwindled, leading to the evaporation and dispersal of its water by the solar wind. The absence of our geomagnetic field could potentially result in the demise of Earth's atmosphere, oceans, and life. Prior to the complete atmospheric depletion, animal life on Earth would be significantly impacted. Beyond humans, various creatures, including birds, sea turtles, lobsters, honeybees, salmon, and even fruit flies, rely on the Earth's magnetic field for navigation through built-in biological compasses known as magnetoreceptors. This magnetic guidance plays a crucial role in the migration of birds to warmer climates during winter, the oceanic navigation of sea turtles, and the location of beaches for egg laying. For instance, female sea turtles returning to the same beaches annually are attributed in part to their innate compasses. The potential disappearance of the Earth's magnetic field poses a serious threat to these animals. Sea turtles may lose their way at sea, migratory birds could deviate from their intended paths, risking their lives, and honeybees might experience disorientation, impacting flower and plant pollination. The decline in navigational abilities could lead to the extinction of these and numerous other organisms. Beyond the search for monopoles, Cern is associated with many other missions to uncover the mysteries of the universe. The Cern IceCube mission, located in the South Pole, for instance, is a neutrino observatory that aims to unravel the mysteries surrounding these subatomic particles. The observatory employs a cubic kilometer array of sensors embedded in the Antarctic ice to detect neutrinos, providing valuable insights into high-energy astrophysical phenomena. Neutrinos are incredibly small and neutral particles, making them challenging to detect. The setup at the South Pole involves strategically placing sensors in the ice, allowing scientists to capture the rare interactions of neutrinos. Unlike traditional observatories, which rely on light or other forms of radiation, IceCube focuses on studying neutrinos, providing a unique perspective on the universe. The Antarctic location is crucial for this mission. The clear, pristine ice serves as an ideal medium for detecting neutrinos. The vast and remote nature of the South Pole minimizes interference from other sources, creating a quiet environment essential for studying these faint signals from deep space. The primary goal of the IceCube mission is to understand the nature of neutrinos and their role in the cosmos. Neutrinos are produced in various astrophysical processes, including supernova, black holes, and other high-energy events. By capturing and analyzing neutrinos, scientists can gain insights into the most energetic and distant phenomena in the universe. The cubic kilometer array consists of thousands of optical sensors distributed throughout the ice. When a neutrino interacts with the ice, it produces secondary particles and light. The sensors detect this faint light, allowing scientists to reconstruct the properties of the incoming neutrinos. This information is invaluable for studying the origin and behavior of these elusive particles. Over the years, Cern has played a significant role in our understanding of the universe and its mysteries. Renowned physicist Brian Cox, known for his work with the Large Hadron Collider, has declared that the scientific evidence for the LHC disproves the existence of ghosts and the paranormal. Brian Cox's assertion is grounded in the LHC's capability to detect the tiniest bursts of energy in particle collisions, making any energy signatures from paranormal entities easily detectable. During a BBC Radio 4 broadcast, he explained that for patterns carrying information about living cells to persist, a medium interacting with the matter particles in our bodies would need to be specified. He emphasized the near impossibility of such an extension to the standard model of particle physics escaping detection at the energy scales typical of particle interactions in our bodies. Now let's hear your thoughts in the comment section below. Thanks for watching, and please stay tuned.